Swayam Prabha. Digital India. Educated India.
Friends, welcome you again to this class of pipe flow. We have already discussed one class on this pipe flow and we will be continuing on our discussion on this particular issue. We started with the topic that how loss of energy in pipe is important, and we will be continuing from that, how we can find some mathematical expression for that also will be discussed today. Well, we were starting in the last class with that importance of assessing friction parameter in pipe. Well, then we were talking about for actually in fact to get that particular topic in more detail, that to assess the friction parameter, we were discussing on how shear stress varies within the pipe diameter, within the pipe section, and then we were discussing how velocity varies within the section in a pipe. And then with the help of these relationship, that is shear stress and velocity, then finally we tried to get a relationship how the friction loss can be assessed. And so we obtained the friction formula in laminar flow that we call as Hazen-Poiseuille equation. And today we will be starting with another general equation that we call as Darcy-Weisbach equation. Well, so this Darcy-Weisbach equation today we shall be discussing. This can be called as a general equation of head loss in pipe. Well, let us consider this, suppose a pipe and the length of this pipe be L, length of this pipe be L, and say the diameter of the pipe be D, diameter of the pipe be D here. Well, on the upstream side there will be definitely pressure force from this side, and from the downstream side there will be also pressure force from this side, and so we need to equate these pressures, and then not equate, rather we need to see how much pressure force from this side, how much pressure force from the downstream side, and also we need to see what is the shear force exerted because of the shear stress tau 0 at the boundary. Well, and the liquid is flowing, so velocity here is V1 and velocity that is flowing at this point is V2. Of course, as we did discuss earlier also, in a pipe if the diameter of the pipe is not changing, it is a uniform cross section, then this V1 and V2 will remain same, and the elevation height of this particular point 1, we can refer this as 1, this is a 2. Well, the elevation for this particular point is Z1 and elevation to the second section is Z2. And let us consider the depth, the weight of this fluid. Suppose this pipe is carrying all this fluid and weight of the fluid is acting in the vertical direction, and if this angle is theta, then we know that another force, that is the weight of the fluid, is also acting, and the component of this weight in this direction we can always write as W cos theta, because our pipe is inclined here and we are taking the angle with the vertical here. So, this force is W cos theta. Now, let us see what is the head loss. What is the head loss? Okay, so total head here will be something, and with that head, well, I forgot to write about the pressure here. So pressure acting here is P, and pressure acting from this side is P2. This is P1 and this is P2. Well, then let us write down the head at this point and head at this point, and the difference between the head in fact is the head drop or drop in head. So what we can write, and that is what the hydraulic loss in hydraulic head. So we can write that head loss HL, head loss, let me write the head loss HL is equal to, say, head at this point we will be writing P1 by W, okay, P1 by W plus, say, V1 square by twice G plus Z1. This is the total head at the section 1 minus the head at the section 2. So this will be P2 by W plus V2 square by twice G plus the Z2, and this is what our head loss is. Well, now as the section is same, so considering uniform section, what we can have, considering uniform section, if the section is uniform section, then we have that V1 is equal to V2 because the charge is same. So if the charge is same, V1 is equal to V2, then we get that head loss is equal to, let me write the head loss here, that HL head loss is equal to P1 by W plus Z1 minus P2 by W plus Z2. Well, so this is the head loss. Now, just if we get in this form, it is not sufficient. We need to have this in a different form so that we can directly apply the equation. So applying the relationship considering, say, balance of forces, equilibrium of forces, what we can write? Well, so applying force balance, what we can write? For, say, equilibrium condition. So from the upstream side, if the sectional area, if the cross sectional area of this section is, say, A1, and then cross sectional area of, say, this section is A2, of course we know that A1 is equal to A2 is equal to pi d square by 4. Well, now what will be the pressure force from this side? P1 into pi d square by 4. And what is the pressure force from that side, that is downstream side, will be, say, P2 into pi d square by 4. So difference in pressure force we can definitely write as, well, let me write here first as, say, P1A minus P2A, that is A is same. Then what about the shear stress? The shear force, the stress is tau 0. So what is the total area? Pi d is the perimeter. Pi d is the perimeter here. So pi d multiplied by the length, that will give us the surface area. As such, say, when we talk about the shear force or the shear resistance offered, this will be, we can write as, say, tau 0 into pi d L. And then of course another force, as we say here, another force is the W cos theta, which is acting in the downstream direction. So this W cos theta will have to be added. Okay. So plus W cos theta, this is equal to 0. Well, just rewriting this part, what we can write, that P1 minus P2 into pi d square by 4 minus tau 0 pi d L plus Now say what will be this weight? What will be this weight? Weight is nothing but the volume of the liquid here, which is again equal to pi d square by 4, means sectional area into length, multiplied by its unit weight. So and that will give us the W, and then its component in this direction we will have to take. So what we can write, that W, that is unit weight of the fluid, and then pi d square by 4 and length, area into length, and that we can have. And of course what we have, this cos theta, that cos theta we can write as in terms of z. What is that theta? If cos theta we can write, say there is a difference between these two level, there is a difference between these two level. That difference is nothing but say z1 minus z2. So this difference is there. And what is this length? So this angle means this angle. So this angle, cos of this angle is nothing but, say we can have this total length L, this is the hypotenuse, and then we can have this z1 minus z2 divided. So we will be getting the cos theta. Okay. So that way what the cos theta we can write into z1 minus z2 divided by the length is equal to 0. Okay. Then if we simplify this relation, simplifying, what we can get, say P1 minus P2 by W, well that we are writing, plus say Z1 minus Z2, that will be equal to, 4 tau 0 L divided by W into D. So that will be the relation. And now in fact this particular expression P1 minus P2 by W and Z1 minus Z2, this is giving in fact the total difference of this one, and that's why this is nothing but the head loss. What we can have, that we already wrote these things, head loss is equal to this part, and that if we here just we are writing say P1 by W minus P2 by W and then plus Z1 minus Z2. So this is nothing but the head loss. So we can write thus that head loss HL equal to 4 tau 0 L by W D. Well, from this expression we can again rewrite this into a different form. Well, that can be written as say 4 tau 0, why we are writing that, we have a definite intention, is equal to HL, head loss we are writing on this side, into W into D by L. 4 tau 0 is equal to WD HL by L. Okay. Well, now this 4 tau 0 means we are writing about the shear stress. This 4 tau 0 means this tau 0 is coming from the property of the surface of the pipe and then other property of the fluid, combined effect, that is which is basically influencing the entire resistance. So this is giving that resistance property. And as we did discuss earlier also, that this resistance depends on the square of the velocity in turbulent flow. So that way, considering all these issues, if we divide it by, let us divide the expression dividing by rho v square by 2. Rho v square by 2 if we divide, that will give us say 4 tau 0 divided by rho v square by 2, and that expression we write as in fact F. That expression we write as F. And then this is equal to, here also we will have to divide it by HLWD, then divided by rho v square by 2, rho v square by 2. Well, now this expression can be now written as say HL. Now our interest is from this expression. Well, this we should know that this is what we are writing as F, and this F is called friction factor. Well, this F is called friction factor, and just from this relation we can now write what is head loss. What is head loss, that can be written. So HL, well, let me keep that expression also here. We are writing that F is equal to HL then WD by rho V square by, well, HLWD by rho V square by 2, and L should have been here. Yes, L is here, so L rho V square by 2. Okay, so that we can write as L rho V square by 2, and from here we can write HL is equal to, say, FL V square, we are writing capital L here, so FL V square, then rho, W by rho is nothing but G, so we can write twice GD, FL V square by twice GD, and that is the very popular expression which is commonly used in pipe flow, and this particular equation is known as Darcy's-Weisbach equation. Okay, this is known as, say, Darcy's-Weisbach equation, and this equation is used for determining friction loss in pipe, where friction factor is very important parameter. Then how to know this friction factor, that is again a issue, and different scientists has in fact worked on that for finding what can be the value of friction factor. Well, at this point I want to just say another point, that in laminar flow when we were discussing, then we got one expression, that HL, Hazen-Poiseuille equation, that we are referring again, that we got that HL is equal to 32 mu VL WD square. We got this expression. Now, if we just write this expression, this is for laminar flow, this is for laminar flow, this is for laminar flow. Now, if we write this equation in the form of this equation, that is Darcy-Weisbach equation, what we will be getting? Say HL, if we write, and then first let me write here FL V square, that is F we are not writing, just we are writing L V square by twice GD. Now, when we are writing this, that L V square by twice GD, then of course in place of V we are writing V square, so we are putting 1 V here, and then in place of diameter, okay, this D also let me write capital, because we are writing here capital D to represent diameter. Well, we are writing D here, so in place of D, in place of D square we are writing D here, so 1 D we will have to write here, and then we are writing, we have not written mu here, so we will have to write the mu here, and as such if we just change this, if we just rewrite this expression, say L we are writing fine, then V we are writing 1, so we are writing 1 V here, then mu we are mu here we are not writing, so we will have to write the mu divided by mu, so we will be writing it here. Just 1 minute. From this part. So, we are writing this expression here, and then what the value we have not written here, if we put all those in this part, then it will be coming, say 132 is here, there, and 2 we are writing here, so this will become 64, and this part will become say rho V D by mu. Now, if we just check, we will be finally ultimately, if we combine these things, we will be getting this expression. So, what this value is, rho V D by mu, this is nothing but the Reynolds number. So we can write that HL is equal to 64 by Reynolds number into LV square by twice GT. Now if we just compare this and that, this equation and that equation, then what we will be finding, this implies what, that F is we are replacing by 64 by RE. So in laminar flow we get that friction factor is equal to 64 by RE, that is friction factor is inversely proportional to the RE. So in laminar flow it is not influenced by frictional roughness of the pipe, that what we did discuss earlier in the last class. That same things we can establish from this relation, that we are getting only it is related to the Reynolds number. So it is here the frictional characteristic is not coming, or so frictional roughness of the side is not coming, pipe boundary is not coming. So we can write F is equal to 64 by RE. It is thus inversely proportional. Well, then let us see how we can get this value of friction factor. Otherwise, say these equations whenever we are using, so this value of friction factor is of great importance. Otherwise, we are not being able to apply this equation. Well, so experiment on friction factor that was conducted, lot of experiments were conducted rather by different scientists. Say out of that we should take name of Darcy, then Nicoretze, Moody, then all they did experimentation to study influence of various parameters on friction factor. Well, and well, all this discussion we are not taking here, we are not covering in this particular class, because well, in fluid mechanics we are supposed to do these things in details, but just as we are discussing about the friction factor, we are taking some of these issues and just we are recalling those issues which we should have studied in our, say, fluid mechanics. And then Nicoretze, he did experimentation on pipe, then how to take roughness, he artificially roughened by sand grain. He make artificial roughness into the pipe using the sand grain, and then for the roughness value, generally the symbol used is epsilon, that roughness value he considered to be the diameter of the pipe. So the grain diameter, this grain diameter means the sand grain diameter, that sand used for, say, making the pipe rough. Inside of the pipe the sand layers were given, and that way he could get the roughness of the pipe. And then what roughness he will be taking, what the actual value of the roughness he will be taking, the epsilon value what he will be taking, he took that as a diameter of the sand grain. So that way he conducted experiment, and then he found, say, a graph relating all those different values. Well, and let me just draw the graph in a very rough way so that we can have some idea. Okay, just 1 minute. Start. So he draw the graph, plotted those value, say, on this side. In fact, Nicoretze conducted this experiment, and Stanton's, these curves are known as Stanton's curve because he also did this work, and then finally he plotted those curves in this form. That is why it is also known as Stanton's diagram. And on this side it is, say, 0.01, then friction factor, that means here is the friction factor value 0.02, then up to 0.1, it is. So this value were there, and then on this side it is Reynolds number, which is going like, say, 10 to the power 3, then in log scale all this 10 to the power 4, then 10 to the power 5, like that, 10 to the power 6. And what they could observe, that when the Reynolds number is low, say we did discuss up to 2000 it remains laminar. So for a low Reynolds number, the friction factor value varies linearly, like that. It will be coming in this form. It is varying linearly, friction factor with Reynolds number. So as we got in this relation that friction factor varies linearly with Reynolds number, of course inversely, and that relation is indicated by our graph here. And of course, we will be putting some dotted point here because now it is in transition. And then till this point, till Reynolds number is lower, say between 2000, less than 2000, then the roughness is not influencing. But gradually this roughness will start influencing. Say we can have a curve like this. So for a value of say epsilon by d, epsilon is the roughness and d is the diameter, for suppose it is very small roughness, say 1 by 1000 around. That means epsilon, if the diameter of the pipe is 1000, then roughness is only 1. Okay. So it is a very small roughness, but still roughness is becoming significant, or it is influencing the curve when this Reynolds number is increasing, or we can say that when the flow is becoming turbulent. Okay. So that way this is going like that. Then with more roughness, our value is increasing like that, curves are changing like that, curves will be like that. Say for E by epsilon by d, large epsilon by d value maybe say 1 by 30. If diameter is 30, then suppose roughness is 1, then we get this sort of curve. Now this sort of curves can be used, these curves are popularly known as Stanton's curve, and these curves can be used for, suppose once we know the Reynolds number, once we know the roughness of the pipe, then we can have the value of this friction factor. Say for that Reynolds number, we will come to this curve and we will be seeing what the friction factor based on this particular roughness. Then again another point at what this epsilon value will be. Again Moody's conducted different experimentation on this issue, and he also gave his own sets of curve. Then he provided a table for, in fact, this roughness value for different material. If the material is wood, if the material is steel, so for different type of wood was not there. Steel, if the material is steel, if the material is concrete, then for different type of material what will be this roughness value. So that was also given, and then it become convenient to use this relation. So we knowing the material, we can take a value of roughness. Of course all these basically need experimentation, and so what can be suggested, though these curves are available, fine, if you do not have any other way out, you will have to follow this curve to find the value of friction factor, because the friction factor is the most important parameter. It is FL V square by twice GD. We got the equation, and here of course there may be another confusing point, that this Darcy-Weisbach equation, we call that FL V square by twice GD. It is fine, but in many books, that as we can see that we are replacing this term, we are replacing this 4T0 by rho V square by 2. If we take this 4 on the other side, that then this equation can also be written as, say HL is equal to 4FL V square by twice GD. I mean, some people prefer to use this equation, that is why 4 should be, they want to show the 4 explicitly, but in a sense that friction factor, so of course we will have to give another name, say F dash, and this equation is known as Fanning's equation. This equation, and some people prefer to show this 4 explicitly, which is coming here, this 4, and however some people feel that as the friction factor ultimately it is a constant, so we can show it just as F1 value. So both the equations are used, and when we are using, why I am just emphasizing this point, because value of friction factor is very important, and when we will be using the value of friction factor, then suppose we are getting the friction factor value for the expression this one, and then this value if we take and if we apply here, then the head loss that we will be getting will be on lower side, it will be underestimated. So we should know that for which formula actually this friction factor value is being given. and that friction factor only we should use appropriately. We should be very much careful, and when we do not have any other way, we will have to take recourse to this curve. In fact, Moody has also given some curves. The Moody's curve is also very popular, that also we can use. And then we have some explicit formula. We have some explicit formula that is relating RE, some explicit formula of f. Generally it comes in the form of 1 by root f is equal to, which is a function of this I am writing function, so phi I am writing. It is a function of Reynolds number, then epsilon by d. So as a function of all those, some logarithmic relation can be developed, and different investigators have given from their experiment different expression for that, say and Colebrook give one equation like that. In the Jain we get another equation in the Jain book. So that way, that sort of expressions are there, and we can use these equations also for calculating the f value using Reynolds number and this roughness ratio, so roughness by diameter. And but now, although all these things are available, what is necessary, that if we have a device with us and we know that this particular pipe will be used for a particular work, if possible we can conduct laboratory experimentation and we can find very easily what the friction loss is. That sort of experimentation is not that difficult. Say we can fix the pipe, and we can allow the water to flow from here to here, and then from these 2 points, suppose any 2 section, we can fix a manometer, and using that manometer we can see the difference in the pressure level, mercury level here, and then from that we can find out what is the head loss. So if we do that, then we will be more convincingly we will be getting the friction factor value. Well, so just I tried to emphasize what the value of friction factor, and the reason is that energy loss in pipe, generally we divide it into 2 parts. One is major loss, another is minor loss, and the major loss is basically coming from the friction loss. So that is why if we calculate this friction factor wrongly, our entire effort will go wrong. Okay. So of course, now when some company they provide the pipe, okay, their pipe is this one, and then they specify what the friction factor value is for that particular pipe. That way also in the market, when we purchase pipe, this may be available. Okay. Then say major loss, as I have explained, the energy loss we can divide into 2 parts, that is the loss caused by the friction, and then there are some minor loss. And of course, this major loss, one characteristic is that this loss is due to constant velocity. When the water is flowing in a pipe, there is no change of velocity, still there we are finding that head loss is occurring. So this sort of loss is also called as constant velocity loss, constant velocity head loss. Well, then well, and minor loss. Minor losses are losses that occur due to change in velocity. So minor loss are that which are very small as compared to the major loss, but and these losses occurs generally due to change in velocity. In the pipe, because of many reasons, the velocity there can be change in velocity, and because of change in velocity, this sort of loss occur. Of course, say we can list the minor loss, and there we will find that one loss which is called the loss at exit at the pipe. So when a pipe is carrying water at the exit point here, so ultimately the water is getting released at this point. At the exit point, there is a loss. Although in this case velocity is not changing, whatever velocity is coming here, it is going out with the same velocity, but still there is a loss which is small in value as compared to the friction loss, and that particular loss we put in minor loss, and but this loss is for constant velocity head loss. And then other minor losses are variable velocity head loss. So due to sudden enlargement of the pipe. Well, say a pipe is like this and there is a sudden enlargement in the pipe, then there will be head loss in the pipe. So water is flowing like this and then there will be some degeneration like that, and then this will cause lot of some amount of head loss here. And due to sudden contraction, so if there is a contraction like this, then also there is a head loss. So in a pipe system we should try to avoid this sort of contraction or enlargement if possible, but definitely we cannot do that. We require this sort of contraction and enlargement. And now as we require this sort of contraction and enlargement, so we will have to know that how much energy will be lost at that particular point. And of course the loss in contraction is less than the loss in this sudden enlargement. Then loss at entrance to the pipe, suppose there is a reservoir, from here the pipe is water is entering, so at the entry point itself some loss is there. And due to gradual contraction and enlargement, well, we have already told about the contraction and enlargement, but if this is gradual, say it is not abrupt, rather it is expanding like this, then also there will be some loss. And if contraction is gradual like this, there will be some loss, but this will be definitely different from this one. Then loss at bend, in a pipe we will be having this sort of bend, and if there is a bend, then there will be loss of energy at that point. So how many bends are there, depending on that we will have to calculate the loss of energy, and we should avoid bend wherever possible. And loss of various fittings, as we know that to regulate the flow we need to use valve. Well, at some point we use some T-section, so these sort of various fittings we use there, and those fittings, when the water is flowing through those fittings, there will be change in diameter at those point to some extent, and those fittings also there is a loss of energy in those fittings, and all these are coming under minor loss. Well, now we can just discuss about loss due to sudden enlargement first. Well, so when we talk about loss due to sudden enlargement, let me draw a diagram. You can concentrate into the slide that say this is the enlarged section. Okay, pipe section has enlarged in this way. Well, now how the water will be flowing in it? Say water is flowing from this side, and then it is moving like this, and it is again going to that point. And when water get expanded like this, there will be low pressure in this portion as compared to here, and there will be deformation, and then because of that we will be having loss in this system, and then water is flowing like this. Now if we consider just on upstream, although in the diagram it is appearing that we are drawing much ahead, but this is just on upstream of this enlargement. If we take a section 1 and just a downstream of the section where it is flowing full, okay, let me take it here where it is flowing full again. That part is suppose section 2. Flowing full means here also it is flowing full, but the streamlines are touching this one, this streamlines which is emerging from here, it is touching at this point. So this is section 2. Then say water velocity here is V2. In this part, unlike the earlier discussion, velocity here is changing. Here the velocity is V1, here the velocity is V2. So head loss due to variable head is now variable velocity is now in question. And say pressure here is P1 and pressure here is P2. Of course, we can write the pressure in that portion what will be. Here it is P1, here it is P2. Let us write for the first case, say let us take it as P dash. Say pressure here, what is acting in the water is say P dash. Well, now what we can write that if we write the energy level between this point and that point, so equating energy, what we can write, say P1 by W plus Z1 plus we are writing in general first v1 square by twice z, but as we are talking about a very small section here from here to here, z value will be in fact equal, because this distance is not that much. Even if it is in inclined position, the z value will be more or less same. So this is equal to p2 by w plus z2 plus v2 square by twice z plus the head loss, and so finally from here what we can write, that head loss, and we are writing 1 to 2, say head loss from 1 to 2 can be written as p1 minus p2 divided by w plus v1 square minus v2 square divided by twice z. So that is what our head loss is, but of course we need a better expression. This expression is saying that our head loss is the difference in pressure head and then velocity head. Well, v2 square by twice c. Fine. Now, from the momentum equation, if we apply, that is the force balance, if we do, from here some force is coming, from here some forces are there, if we try to equate those things, then say if we take this area as A, area suppose as A1 and area here is A2, well, and velocity already we have written as this thing. So what is the momentum say per second or through the section 1, So what is the mass flowing? If rho is the, then area into velocity is the, say, okay, we can write here area into velocity A1 into V1, this is the discharge coming, and then if we multiply it by rho, it is the mass coming, and then mass into velocity if we do, that means this is rho A1 V1 square. So this is what the mass momentum passing through this one, this section 1 per second, then momentum per second through section 2, this is equal to rho A2 V2 square, then rate of change of momentum, we are coming to Newton's equation now. So rate of change of momentum we can write as, say, rho then A2 V2 square minus A1 V1 square. Okay. So this is the change in momentum, which should be equal to applied force. So from Newton's equation what we can write? So forces, now what are the forces? Well, the force we can write as force is equal to P1 A1, this is one force. Then if I consider this pressure to be P dash, then what is the area? This diameter is A2, this area is A2. So A2 is the entire bigger area, that means this bigger area. From here to here there is no change in section. So this is the bigger area. A2 minus, so this area minus this smaller area will give us the area here, this portion of area, and this area multiplied by P dash. Okay, let us write it like that first. That is the A2 minus A1 into P dash and minus P2 A2, and this is equal to the force, so rho A2 V2 square minus A1 V1 square. Fine. And as the fluid at the corner, is at rest, this is at rest, and then here the pressure and the pressure at this point can be considered almost equal, and just at upstream, although we are drawing it far apart, but this P1 is the pressure here. So as this fluid is in rest, so we can consider this pressure and that pressure to be almost same, because the fluid is in rest and it is in contact. So this pressure and that pressure we can, that is the pressure P1 and P dash can be considered to be almost equal. So considering as the fluid at the corner are at rest, so considering, say, P1 is equal to P dash, that we are doing, and then we can just simplify this expression to say A2 into P1 minus P2 is equal to rho A2 V2 square minus A1 V1 square. So what we can write, this is equal to say P1 minus P2. Our basic intention is that we are trying to have an expression for this particular term P1 minus P2 by W. So P1 minus P2 by W, that we can write as rho by W, then V2 square minus A1 by A2 into V1 square, and this we can further simplify to have a relation that say this is equal to, so this rho by W is nothing but 1 by G. So what we can write this as V2 square by G, V2 square by G minus again this A1 by A2. What we can write for that? We know that discharge is same, so we have that A1 V1 is equal to A2 V2. So A1 by A2 is equal to, we can write V2 by V1. So if we write it as V2 by V1, so what we will be having, this expression will become V1 V2 by G. So it is becoming V1 V2 by G. So from P1 minus W by P1 minus P2 by W is now we are expressing in terms of V. Our basic intention is that on the basis of difference in velocity, we are trying to find an expression for head loss. Well, so if it is like that, this we can further simplify, say head loss from 1 to 2 now can be written as V2 square by G minus V1 V2 by G plus V1 square by twice G minus V2 square by twice G. So now this V2 square by twice G minus V2 square by twice V2 square by G minus V2 square by twice G, that this minus half of this, that will become again that we can write as say V2 square by twice G first, then minus V1 V2 by G plus say V1 square by twice G. Well, and that can be written as, now if we take say 1 by twice G common, so this is equal to say 1 by twice G we can bring common, and then what we will be having, V1 square minus twice V1 V2 plus V1 square. This is V2 square. So finally this expression is nothing but V2 minus V1 whole square. This expression is nothing but V2 minus V1 whole square. Well, I am writing this expression here, that is, this can be written like that, that head loss from 1 to 2 can now finally be written as 1 by twice G V1 minus V2 whole square. Well, this equation is known as say Carnot or Borda equation, because as per as they did this. So this equation is popularly used for computing this head loss due to sudden expansion. Well, now when we talk about head loss due to sudden contraction, then this head loss due to sudden contraction is nothing, indirectly we get it from head loss due to sudden enlargement. Let us concentrate on the slide. Well, say if we draw this particular relation for a contraction, just we can see that this is, we can draw in this form. Well, and here water will be coming in this way, and then there will be a contraction like that. Water is entering into the pipe like this, and up to certain extent it will continue flow like this, and then there is a expansion. It will finally meet the level here, and this contracted portion here, that we have minimum area that we write as AC, and it is like that called vena contracta. So that we are getting here, and diameter at this point is, or say area at this point is say A, and the area at this point or this point is same. So this is the area A at this point. So this is section 2, and this is a important section here, this is 3, and let this section be section 1. In fact, the loss is basically due to not because of this contraction part, but because of this expansion part. That is, water is expanding from here to here. That is the very basic reason of the head loss here. And well, as this is the reason, so let us first find what will be the velocity at this point. We know that say velocity here is suppose v, and then what will be the velocity here, say AC, and suppose velocity here we are writing Vc. So AC into Vc is equal to A into V, and this implies that our Vc is equal to A by AC into V, A by AC into V, and this A by AC, in fact, of course, not A by AC, AC by A is called, I mean this is written AC by A, that is given as a coefficient CC, contraction coefficient, say. So this CC we can have here, that AC by A, and that is why we can write this as V by CC. Well, this is what we can have, and then of course we have standard value for this CC. We have some value for this CC for different ratio of say this area and this area. Say if we give this as A2 by A1, then that as proportion to this ratio we can have some value for this CC, and as such this can be used for calculating the value. Now head loss, as we were saying, that head loss is equal to head loss HL, is equal to, so our velocity at this point Vc minus V, because just like it is expansion, I mean 1 by root over 1 by twice g, and this velocity we should write, say, well, let me write first Vc minus V whole square divided by twice g, just like expansion loss from here to here, and Vc is nothing but what we can write V by say Cc minus V whole square divided by twice g. Well, this expression can be used for computing the loss due to sudden contraction. Well, and then we can have, as I said, that we have this sort of ratio, say A2 by A1, if we put say, and then we can have the value of Cc, that is a 0.1, 0.4, 0.7, 1. 1 means this pipe is not having any contraction. So if we get this sort of a table, and then this table gives that this is equal to 0.624 when it is 0.1, A2 by A1. A2 is the downstream point, that one, and that means okay, whatever it is, this is the smaller one, this is the bigger one, okay, A2 by A1. So that's why it is becoming, suppose 10 times this bigger one is 10 times larger, so we are getting 0.1, so it is 0.624. This value is Cc's, and this is 0.659, this is 0.755. With the decrease of this ratio, this coefficient is basically increasing, and then sorry, with the increase of this ratio, this coefficient is increasing. Then when it is 1, then there is no value of this Cc, because there is no contraction. Well, so using that relation we can finally find the value. Of course, generally for most of the cases, if we do not have this sort of I mean chart for a particular situation, then, and for simplicity, because these losses as said that these are minor loss and very small, so generally this head loss HL due to contraction is taken as equal to say 0.5 V square by twice c. V is the velocity. That means indirectly what we can say here, this is V, and Cc value if we put, we will be getting ultimately this in terms of V square by twice z, and of course some other term will be there, is twice V1, V2, that will also become say V square, and some coefficient will be there. So it will be a I mean putting those value will be getting nearly equal to this expression, and then the value can be written approximated as 0.5 V square by twice c. Well, similarly now when we talk about say head loss in entrance. So, head loss at entrance, head loss at entrance. Well, so head loss at entrance, if the entrance point is like that, say entrance point is like that, sharp edge. So, water will be entering like this and then it is flowing here, and this can be considered as 0.5 v square by twice c. So, a very common expression that we use is 0.5 v square by twice c. Well, these are fine, but if we try to reduce, if we think that we need to reduce this head loss, then what we can do, that in a where we have the entry point, then there we need to make rounding of this pipe. So, if we can have our connection in this form, then our head loss will be minimum, then our head loss will be minimum. There will be some head loss, but it will be, if we can round it off. So, round entrance, the head loss will be less. So, if possible, we should make our entry point in this form. Well, then we can have some other losses like loss due to obstruction, loss due to obstruction, loss due to obstruction. Obstruction means this obstruction by what we can mean, that it is the fittings. Suppose any fittings are coming, and in the pipe, as we said, that there can be valve and other things. So, all those when we combine, then we in totality we can say that these are some obstruction to the entire pipe flow system. And for all those obstruction, what we can take the head loss as, this is normally taking a very definite value is difficult. Generally, from our experience, from observation, we should try to estimate what sort of loss that can be, and generally a k value we can say. We are knowing that a coefficient will be definitely coming in terms of change in velocity or normal velocity. If the obstruction is not there, then in the pipe we can have the velocity, suppose v, then the loss will be always proportional to v square by twice c, but there will be some coefficient multiplied by that. So, we express this loss, any loss in this form, say valve, etc. Loss due to obstruction means what we are meaning, it can be valve, etc. And that is HL, head loss, we give as say k v square by twice c. And this k is the coefficient that we need to determine, that is determined to be determined experimentally, okay, to be determined experimentally. Well, so that way we did discuss already about some of the losses, the pattern of losses, and we have listed some minor losses. If we go back to our this point, that loss due to entrance in pipe, that we have discussed explicitly, loss then due to gradual contraction and enlargement, that point what we did mention, in fact, as if we are rounding off. So, when it is a gradual contraction, then this sort of abrupt change is not there. So, eddy formation and those sort of things are coming less. And when in a pipe system we can make a gradual change, whether it is contraction or expansion, then we can reduce the head loss. And of course, if a pipe is tapering, this is the changes. If a pipe is tapering, here we should not confuse with this part, that gradual expansion and enlargement. If the pipe is tapering, well, loss in band is also like that. We need to keep a k value, and then we need to determine this loss in band, and by experimentally we should determine it. And fittings, already we have mentioned that. And say when we are talking about loss due to say gradual contraction, then there is another issue, that if a pipe itself is contracting like this, if a pipe itself is contracting, tapering pipe, well, the pipe is tapering, and in that case the friction formula that we are using, that FL V square by twice ZD, will not be straightway applicable. We need to take care of the area, because area is changing. Here suppose area is A1 and here the area is A2, then this sort of changes we need to consider, that is, it is tapering, and that we can find out by applying the principle that for a small elementary length, say dA, we can find out what is the for a small elementary length, say dx, we can find out the what will be the area from A1 to A2 if it is like that at a distance dx, at a distance x, for a small elementary dx, what will be the area we can find out, and that way for a length of dx how much would be the head loss, that we can find out, and then to find out the total head loss from here to here, and for finding the head loss here we can use the formula FL V square by twice Z, because it is a small length and change in say area between these 2 points is not that much significant. So, we can write FL V square by twice Z here, but the L, what is that? L will be dx here, and then velocity, of course, we will have to take V based on the area ratio, and then we can find out with the friction characteristic F, we can find out this value, and then finally to get the total head loss we need to integrate it from this area to that area, and then we will be getting what is the head loss in this sort of pipe. Okay. Well, so in this particular class we have tried to see that in a pipe system, apart from the friction loss, what are the other kind of loss that we can have. And of course, initially we have discussed the loss due to friction, which is a major loss, and we have a general formula for friction loss, that is FL V square by twice Z, which can be applied. But while applying, it is an easy formula we can apply, but for applying this formula the value of F is very important, and that is why we have also discussed from where we can have this value of F. Sets of curves are available, Modi's curve, or say curve given that we have already discussed here, the Stanton's curve, and so that way curves are available. Similarly, some formula are also available, explicit formulas are available, that if we know the Reynolds number value, if we know the roughness value, then we can calculate the friction factor directly by using some explicit formula. So, with all those formula we can find the value of F, but still if we are not confident and suppose our problem is very much important and very sensitive, then we should know about the friction value directly by experimentation, and we can develop a setup. Developing a setup for conducting that experiment is also not that difficult. So, we can develop a setup for conducting experiment for finding the friction factor value of different pipes, and then that we can use. Of course, company which produce pipe, they also provide some frictional characteristic of the pipe, friction factor value they also provide. But for very precise work we need to know this friction factor ourselves, and then knowing the friction factor we will be getting the energy loss due to friction. And apart from that, in our entire system there will be lots of bands, there will be lots of enlargement, there will be lots of valves, and for all those enlargement, contraction, valves and bands, we will be having some sort of loss that are of course very small as compared to the friction loss in the pipe, but those losses we termed as minor loss, and at the exit, at the entry also we have some loss. But one important point is that minor loss are of course not that significant when our length of the pipe is very large. In a very large pipe system where length is very large, this minor loss, if the joints and these things are less, then we can neglect. But if the pipe system is not that long, if our length of the pipe is not that long, and then in that case say a minor loss doesn't become insignificant, then we have to consider the minor loss, because major loss is less when the pipe length is less, and that is why then the minor loss also become dominant. Well, with this we have understood some of the issues related to friction factor and calculating head loss. Then using these In the next class, we will be going for discussing some more topic in pipe flow. Thank you very much.